Welcome back, everybody. It's time to start next lecture. Today we are going to finish discussing on this topic on point cloud alignment that we started last time. And then I'm going to introduce briefly the topic on mapping, right? So, well, basically it's going to be two parts in this class. First of all, let's do a brief summary of what we did last day. Basically, we were talking about differentiation. Okay, differentiation. Right, so we were discussing exactly what it takes to differentiate with respect to a group of matrices. Right, it's not that easy just to apply standard derivation rules, but there was like some little problems. One of them was related to this, right? So we cannot really differentiate with respect to, this is basically a rigid body transformation, so it was not possible to directly differentiate against this. So what we did instead is, on this first approach, we were transforming this input. Now instead of being a transformation, right, it was this composition of two rigid body transformations, right? And we have discussed, like 2 lectures ago, that actually this is a very nice property of rigid body transformations. So you can just chain 2 rigid body transformations and you will get still a rigid body transformation, right? So the solution for us was that we define a small increment over this transformation, and then what we are going to be seeing is how this function changed, this new function. Now the input is just this little increment with respect to the previous point here. With respect to these coordinates in the manifold, right? So, and then we discussed a little more. We proposed like some solutions for some known problems. For instance, this problem, right, transforming a vector. And this is what we did on the second part of the class, right? On the seminar, then we gave you some points, and the problem was, okay, find the transformation for this. Has anybody tried to solve it before the solution? Has anybody run the solution? No? What? You only do problem set 3. That's all you have. Okay, that's fair enough. That's fair enough. So you will have a solution. You have a solution already in Canvas somewhere. I think in one of the announcements. So if you want to find out how to solve this, just go there, check a little the code, what you had before on the seminar, what is the solution, and with that I think some of the things will be, some of the unclear issues on this seminar will be a little easier, little more clear. Again, this is going to be the basic for problem set 4, so if you have done the seminar and if you run this code, you're probably done almost 50% of problem set 4, probably more. Yeah, probably more. So that's good. Well, now you haven't run this, but I believe you think that this is a good idea just to calculate gradients with respect to transformations directly, right? So you could be proposing like different solutions to minimize this kind of summation of residuals. But what we have explained directly calculating gradients with respect to this transformation is, well, a good solution, right? And it doesn't require you to break down the problem into parts, rotation and translation, and doing other strange things. It's just, you know, you just calculate the gradient and that's it. Okay, so I guess you haven't tried the solution, so that means that most of the questions are going to be on problem set 3. You are in good terms in problem set 3? Who has finished problem set 3? Okay, okay. I guess, yes, we will answer anyway questions that you have with respect to this in the break, after class. But if you haven't started, well, those that haven't finished, how much is left? How much? 10%, 20%, 40%? Okay. Okay, well, that's something. Well, we'll be here answering questions by the end of the class, right, regarding problem set 3. But there's a lot of little details and technicalities. So you just need to be aware of them. Okay, let's start this second part, what we didn't finish on the previous lecture, on point cloud alignment. Or also, this is called point cloud registration. Okay, so we were defining point clouds, right? Point clouds can be in 2 dimensions, 3 dimensions, doesn't matter. In our seminar, we were using 3-dimensional data, but this is also true for 2 dimensions, right? So consider the following example. And this was quite popular like some years ago, where sensing was not so powerful as today. We didn't have like all these 3D sensing, all RGBDs that didn't exist, right? So the most accurate sensor back then was laser, and before that was ultrasound. So still, you can get very good information about the environment, but it was slightly different, right? And in this case, most of these sensors were 2-dimensional sensors, right? So then, back then, when you had these robots, or you were moving on a, let's say, on this kind of environment, right? What you will be seeing is something like this. So if this is a 2-dimensional range, I'm going to now simulate like all measurements that you should be getting. It should look something like this. So imagine you have a bunch of lasers or whatever other thing. You are measuring distances, and then basically these rangefinders were giving you this. We have discussed in this course a lot about landmarks, right? But landmarks is just a way to extract features from these point clouds, right? Whatever comes from the information, landmarks can be seen as just a process output of these sensors, right? So if you had more points, maybe here you can define a corner, right? If you had like these points here, maybe you can align and define a line. That's up to you, right? Mostly we have discussed about point landmarks, right? But there's other kind of landmarks out there. Okay, so this is what we have. Like, let's say if we are simulating our sensor. Right? It's just going to be a set of points, right? Right? So now, forget about landmarks. In this lecture, we are going to discuss a little more just about point clouds, right? So our observations are going to be just raw points. Seminar was a little about this, right? So we were giving you a bunch of points, and then you need to find what is the transformation. So this was like we were advancing a little the topic of today. Right? But the idea is going to be very similar always. We have a couple of observations, how they are connected. Right? This is what we are going to be discussing today. So these are points, in this case in 2D. So imagine here you have P1, right? P1, if they are just in Euclidean coordinates, it will be x and y. We have also discussed that another alternative might be range and B-ring, right? So this is, from the physical perspective, this is the time, well, you are measuring with a laser or with another device how far away is an object. In this case, you trace a line. Imagine you have a laser and you are measuring when you hit an object and the signal gets back, right? So what you are measuring is this time of flight, kind of. No, this will be, let's say that here we are just in this time index, right? So then you will have different sets of points for a different instant of time, where probably your robot has moved. So think about this if you want a temporal index. Yes, another question?
So one observation is a set of points.
Yes. this is our observation, this set of points, but we are going to call them now point clouds, right? It could be 2D. In the seminar, you were already working with them, but the idea is the same. So whatever your sensor is giving you, you are going to process it, right? Okay, so what is the problem then? So we want to find a transformation. In this case, this transformation from a pair of poses, right? Imagine now it's not just xi, but we have a second pose, right? And imagine if you move a little, this pose changes, then the observation that you will get, all this set of points, all this point cloud is going to be different, right? So this was a little what we were discussing the other day on the seminar, but now it's a little more general or a little more formal, right? And then basically the solution is going to look like this. So we are going to have a transformation from frame I to frame j, right? So remember that poses are also expressing frames, right? That's an alternative. Well, another utility of poses, right, that they also explain frames and they also transform points from different frames. So that's very useful. We discussed a lot on this 2 lectures ago. And then we basically take all these points. And after this transformation, which is a rotation and a translation, you should be getting, if we were observing the same points, which that's not always true, we should be getting exactly the same observations, right? From one frame and from the other frame transform. Okay, so yes, that's clear. So I'm going to write here maybe this thing. Oh, that's a bad color. xj, right? So you are changing, and this is what we are measuring here. Okay, is this problem like now clear, well defined? Because we are just going to be discussing about this in the first part of the lecture. We started, if you remember last day, discussing about gradients, and you will see in a moment where this is going to be useful, right? All these optimizations where we need gradients is going to be useful for calculating this transformation. But it's not the only way to solve this problem. Okay, so as I said, this problem is registration or alignment. For now, it's very general, right? I'm not saying if this is 2 dimensions, 3 dimensions, whatever. But, well, this, by the way, this should be in homogeneous coordinates. But it's not the first time that we do this some sort of relaxed notation, right? Where we are just putting points, but actually we know that to be transformed, basically what we need is a 4-dimensional vector, or, well, basically whatever dimension plus 1. Okay, so now this definition considers 2 unrealistic things, right? So the first one is, let's say, assumptions, right? So number 1 is point correspondences are correct. That was the seminar, right? The problem in the seminar, but that's not always going to be true. For that, then you can do a lot of things. Data association, we have discussed on this. Maybe like providing descriptors in your features. There's whole things that, well, I'm not going to discuss, but you need to think that this is not always going to be true, right? Point correspondences, well, this is a strong assumption. But for start understanding the problem, I think it's an initial, good initial point. Okay, and what is the second assumption that we are doing if we have this thing perfectly set? Is that, yes, basically our observations are sampling exactly the same points. So what does this mean? In an ideal world, yes, you have this problem and it's very clear, right? If you had the same and all of them are just related by some transformation. But in a real world, let me retrace this thing a little. So you will see that whatever the geometry is, we are not going to be sampling exactly the same points. Right? We are not sampling them because the robot has moved, because the sensor has like some, I don't know, maybe it has like a fixed step where things are moving, so it's not possible to sample exactly the same points, right? You see that here, some of these points are going to be different. So, I mean, exact points will require all of them to be here, right? But we know that that's not possible. So given this configuration, given this orientation and the sensor, whatever it is, maybe it's constant step, for sure it's going to be very hard to observe exactly the same point, right? What are the chances of having a surface and sampling the same point? Not much, actually 0. But, well, in theory 0, in practical maybe it's not that. Okay, well, that doesn't matter. But the problem is that these points are not the same, right? So then what we need to do is do a transformation of something that we know that it's not exactly observing the same entities, right? There's going to be some noise. If you have here a lot of density, maybe the point is, I mean, the difference between points is small, but still there's going to be something, right? So then we will need to consider noise, right? We need to consider this as a random variable on why we are not sampling the same point. Okay. So we introduce a random variable, and then we'll see that the problem changes slightly, right? So this is never going to equal. These 2 points, they are going to have some error, some residual, right? This is an over-constrained problem. So we cannot make them, all of them, equal. Well, but this is the problem of estimation, right, in general. So you always have a lot of observations, more than required, and then the problem is doing your best estimation, right? So it's always solving a over-constrained system. Okay, so, well, based on these 2 assumptions, I think we are going to start relaxing this a little, or being a little more strict, I would say. And then this is the first one that we are going to discuss, right? So we are not sampling exactly the same points. There's going to be like some noise, some random variable, but still we will be calculating solutions, right? Transformation between the point clouds. For now, we assume no correspondences, but this is going to be second topic. Okay, so with this, I'm going to discuss a family of solutions, right, that basically give this transformation, the estimation of this transformation given like these 2 point clouds. We have done one of them, which is based on this, it's basically an optimization one. This is what we did on the seminar, but this other approach is a little different, right? It's based on a different concept. And this is probably closed form solution. You don't need an iterative method. You just have a solution with whatever input you give, right? So it's going to be based on SVD methods. The solution for this, by the way, it's known for some time, like from the 87. So there's some variants of this method, but still, if you just use linear algebra, the solution that you can get it's going to be similar to this. Okay, so as we were saying, we are not considering anymore the perfect points. We are not observing the exact same points. So then what we do, we define a cost function, right? If this was exactly, all these points were exactly sampled the same, I mean, if observations were sampling exactly the same points, this should be 0. But if they are not, then what we can define is this basically error between okay, and for now, I think, yes, we can start with this. Right, so does this look familiar? This was the problem that we defined last day, right? Now we are just reasoning a little more about why this function makes sense, but in essence, what we are trying to do is match all our points from point cloud J to all our points in our point cloud Zi, right? These 2 point clouds, we are trying to match them by finding this transformation that is going to minimize this quantity, right? It's not going to be 0. There's always going to be some point where, and actually, if you run the solution of the last seminar, you will see that this doesn't go to 0, right? It really reduces, but it doesn't go to 0. Why? Because there we assume like some noise on the sampling of points. Okay, so if we have this, then the problem is minimizing the J function. In this case, if this is just a cost function, you can be just doing first-order methods or second-order methods, right, and do an iterative optimization. But this problem is slightly different, right? It's going to exploit a little the some structure of the problem, and then we are going to find a closed solution, right? So in this case, yeah. So this is the exploitation. So we decouple, or no, the method. Translation and rotations. Right, so first we are going to solve one part of the problem, and then we are going to solve the second part. Right, so what is the first part that we solve? Well, indeed, it's first solve the rotation. Right, after doing, basically you need to center all data, and then if you want to take a look at the paper, it's there in Canvas. Right, I think it's couple of pages, so it's interesting, but I'm just going to describe here briefly the idea. So you center all data, and then the solution comes from, let's say that you calculate some sort of cross-correlation, and on this cross-correlation, one of the rotation matrices, let's say that it's one of the U matrices in the SVD decomposition, right? So, well, there's, okay, let me write it this maybe a little better, right? So what I do is this, and then apply SVD and other considerations that the authors are doing, right? So with this, you calculate rotation. For now, let's just say that this is why this is called SVD, right? Because the SVD comes from this cross term, right? We decompose it. And then the second is based on this fact. So if you do the expectation on all these point cloud, whatever it is, right? It's going to be equal to the expectation of the other point cloud, but centered, right? And this center is exactly the translation. Right, so let's say that centers of point clouds correspond to translation. What is the great thing about this method? It's a closed form. You don't need an initial guess. It doesn't matter if you don't want to give an initial guess. You are going to have a solution just applying this algorithm. Another interesting thing is that if you don't have degeneracies, like imagine all points in a line or things like that, you just need 3 points. Right? So with 3 points, you can calculate rigid body transformation. With less points, you cannot really calculate that. And then, well, you always find a solution if, as I said, these points are not degenerate. So this is kind of, it's also very efficient, right? So you just run the algorithm, an SVD, and then whatever solution is. So these kind of solutions are useful, right? They have like some problems, right? So I'm going to discuss them here. So problem is with SVD, they are usually very sensitive to outliers. So if you have an outlier when you are building your covariance, your cross covariance, then things are not going to be exactly the true transformation. So that's a thing to think about. And then, well, this is requires correspondences. Okay, so what else? Do we have another alternative for this? So we can call these energy-based solutions. And we have already discussed this last day. So in this case, what we do is we take this function. We have defined this as a input of what? Point clouds? Yeah. So this function here, right? And then what we are going to do is what we did last day. We are just going to optimize over it, right? And for that, what we have is an iterative method. Right, so if you, why is that the reason? Why is this better than SVD? So as I said, outliers can be like a problem. So with that, you will converge to a solution, and maybe you want to start considering, I don't know, covariances here, or do similar things with what we did, right? When we had like a probabilistic model of your observations. So that's basically, you will get more accurate solutions with usually with optimization-based solutions. So here we have this. And then we just minimize, right? So now what is the great thing? That we know how these gradients look like, right? We know how to update things, right? So this is whatever increment you want, and then here we just have this, right? In this case, remember we were using this. But for second order methods, maybe this alpha is a little different, right? Maybe this is the inverse of the Hessian. Okay, so this is what we discussed. Even if you didn't run the solution, you see what is the other way of solving this problem, right? We started doing this last time. Yes or no? I mean, I see doubts here. Do you think that this is the same problem we did last time? You see it too different? You're still hesitating? No? Okay. Well, take a look. Please run the solution. Run the solution, because then you will see like iterative methods in action, right? So you just have a gradient, you follow that gradient, and that's going to give you a solution. So that's another way of solving this problem. Okay. Now I'm going to talk about the second kind of nature of or let's say this assumption that we did on known correspondences, I'm going to relax it. I'm going to make it a little more, I'm just going to forget about this assumption, and then we need to do like data association problem, right? So in points, it's a little hard to do data association as we described before, and for that, I'm going to describe a new method. There's many alternatives here, but I think this method is really worth it that you know. Maybe you already know about this. So who has heard about Ransack? We have some people not, okay. So this is very general kind of hypothesis testing algorithm, right? You can use this for alignment, but you could use this in any state estimation problem where you don't really have like a clear idea of what is your set of inliers and what is your set of outliers, right? So that means that you don't know if the correspondences were good or they were not good, right? So you will see that this gives you like a good way of working on that. There's also the paper if you want to take a look in Canvas, right? It's also quite old, but it's still very popular. There's a lot of variants on this. Okay, so I'm going to try to do a short version of it, so everyone should understand the idea, right? I'm not going to get into the math or the details, but everyone should understand the idea. And then later, if you are like in a problem that is well solved with Ransack, then you will know, okay, so this is what it's doing. Okay, so all this basically stands for, well, for the following. It's random sample consensus. As I said, it's more general algorithm. It's not really used just for point cloud alignment, but it's used in many other places. And then basically the idea, as I said, is we reject outliers so we are going to sample a subset of points. In our case, it's going to be like points in one point cloud, points in the other point cloud. And then what we are going to do is solve the problem. This, let's say, with this reduced input, we are going to solve the problem, right? And then we are going to do this multiple times, many times. Why? Because these subsets are going to be small subsets. Solving this is easy, right? SVD method gives you a good solution. Kind of good. And then we are going to do hypothesis testing, right? So whatever solution of this set of subset of input, is it giving a good overall solution or is it bad? You do this many times, sampling like, and then you will eventually you will get basically there's an upper bound on the error that you can get on this, right? Yes. So an outlier would be a ground correspondence in this case, right? So you are saying that this point corresponds to this other point. You solve the problem, and then no one actually gives you like a good transformation of this, right? So if you transform all points, then there's going to be like a height error that you are doing, right? So that means that the transformation is not good. So if you sample enough of these subsets, you will eventually find like all these good correspondences. In this case, maybe you have ground correspondences, right? It's not really finding about correspondences, but it's also finding about really outliers, like things that shouldn't be even be like associated, right? So maybe your association algorithm has like a lot of failure, and that's why you need to find like what good associations you have in both point clouds. Okay, so let me grade this again, and then I'm going to grade a little more by sampling. Observation. Okay, so in this case, I'm calling them like this, Z prime, right? And then just to write a little more pseudocode, right? So then things are going to be a little more clear. So in this case, we have discussed an SVD solution. Right? Now, instead of giving like the full point cloud, we give just like a small subset of them. And then we solve whatever solution is this, right? So this is going to give us the solution of this transformation. And then there's a second step, because this, I don't know, if you have 1,000 points on each point cloud, maybe here you're just taking 3 or 5, right? It's basically a subset. And then what you do is you test, right? So you run again your cost function, and then you see if this hypothesis, in this case it's a transformation hypothesis, is good or not, right? So you can think about it as a test, right? Hypothesis test. Okay, and then basically you iterate this as many times as you have budget for, right? Okay, this is the general idea. If you want to see more details, you can take a look at the paper. There's many implementations out there. I'm sure that there's many other explanations, but in general, this is a very good way that doesn't require like a lot of prior knowledge to solve all these kind of problems where you might have like a lot of outliers, wrong associations, or other things that are going to hurt your estimation, right? So with this, you will find like better solutions. Okay, so okay, and then we come to last of these solutions, now absolutely not using any correspondence and not using like sampling known points. So this is with no prior assumption, you just have whatever point cloud it is. And then it's another old method, but it's very, I think, still used today, or variants of this for short, right? It's called iterative closest point. Or ICP. Who has heard about ICP before? We have some people. Okay, so it's also very well-known method. It was not exactly defined in the ways that most people use it today, right? Because it's point-to-point, but actually on the paper they formulate it as a point to surface or point to any other geometric. But the idea, it's not really on that, right? I think the idea is on this thing that there's iterative closest point, right? So you are always looking for the iterative closest point. You solve and then look for the iterative closest point. Right? So this is an iterative process where, since you don't know the data association, you are just going to assume that association is nearest neighbor. And you keep doing this, so association is going to change as you change your transformation. Right? And well, the problem is that yes, local minima is a thing and many other issues, but still there's proofs for convergence, right? Given like, not global convergence, but convergence given like the right conditions. So it's very popular, it has like good grounds, in practice, very used, and there's many variants of this, right? Trying to solve like, okay, so what is the best way, what is the nearest neighbor? This kind of things, right? So there's many variants on this. Okay, so let's discuss it, right? So we have 2 point clouds. And no correspondences. Right? So what we need is we need an initial transformation. So this is always the same, right? So for iterative methods, you always need an initial condition, an initial solution, and from there you start iterating, right? Depending on the problem, it might be very sensitive. So initial conditions might lead you to local minima, right? So that's not always the best case. But in this case, well, let's say that this little problem is compensated by other advantages. Okay, so then what we do is find closest point. Okay, so then we define like the distance between whatever point you want, from frame I if you want, and then all points from frame J. Again, there's efficient ways of doing all these all-to-all distances, right? So you don't really need to go exhaustively against all of them. But well, for now, let's say that you calculate this minimum distance. What is this? So what this means is that, oops, we are looking for the closest point. That means this point that is in this set I point cloud. No, so yeah. Okay, let me write it. Okay, so this minus the given point, right? So this is going to be our given point. This is going to be all other points, right? And basically what we are finding is the minimum, right? This point that is closest to this point, right? So that that means that this point should be in the J, in the other point cloud, right? So this was chosen. We just start with one point, and then you find the closest point. And then, yes, we'll do this for each point, right? So this has to be done n times, right? So it's kind of expensive, but well. Okay. So basically, it's yes, it's single point against all points, right? And then you do this for all points. So it's kind of brute force. There's variants of this, right? So maybe you use like gated trees or other structures, but for now we don't care too much, right? Let's say that yes, this is how we are doing. We find the closest point. We have all this set of closest points. This is going to be our correspondence. Do you remember from data association? What is the first thing that you can do? Nearest neighbor, right? Yes. And then we did nearest neighbor Mahalanobis distance. Yes? No? And then maximum likelihood. Okay, so in this case, it's simpler than that. Just nearest neighbor on our Euclidean distance. And then what we do on the next step is we align point clouds, right? In this case, you could be using whatever you want, right? Like SVD or the energy-based optimization, right? And then, so with this kind of tentative of correspondences, we solve the problem. We have a transformation. And then basically, we iterate. Okay, it doesn't want to work now. Oh. Right, so we go again to the first step. We find again which is the closest point, which might have changed, right? We solve again the problem, and then we see if we have converged, right? So convergence is basically like looking at the cost, if it has changed, or looking at the solution, if it has changed, right? You define a tolerance, that's still an open problem, right? Convergence. You will play a little with that in problem set 4. But, or maybe, yeah, maybe you have a maximum number of iterations, right? Maybe that's your convergence, like a little force. Okay, so in essence, that's ICP, right? I'm gonna, well, there's like a drawing, but yeah, let's do this, right? So we have this point in xi. And then we have this point we have these 3 points. And then what we have is this from this transformation, right? So we have this and this, right? So then we need to find what is the closest point. So maybe for this, this is the closest point, right? And this is at iteration 1. Now, we go at iteration 2. And this point has moved here for whatever reason, right? And this is the idea. Now, these correspondences keep changing as you update your solution. So now this is going to be the closest point, right? And you basically do this until convergence. And this is the good thing about, or one of the contributions of these papers, that there's proof of actually monotonic convergence, right? There's not, I mean, the error should be decreasing all the time. It might stay constant, but still you always get updates. You always get improvements if you follow this algorithm, right? So this has a very nice property. Is this slow? Maybe, right? So what it means that you need a good initial point. So if you don't have a good initial transformation, you might iterate a lot. You might even get up in local minima, right? But still, the algorithm converges. Whatever it is, it's going to converge monotonically. Okay, so I hope that now it's a little, well, at least you have this list. This is kind of a skeleton. We were just presenting methods a little broadly, but this is what you would be doing if you want to align a pair of point clouds, right? You have all these, let's say, little details. Maybe you have non-correspondences because, I don't know, you have very good way of describing your features, or maybe not, and then you try to run RANSAC or ICP, right? Usually the default one is ICP. But now at least you know like some other methods, not just observing landmarks, right? So this is a little beyond that. What happens when you have this, right? So with this, you will have basically a transformation, and this is going to be your observation. So if you remember, what we needed for closing loops is having some function that connects these two things, right? So in this case, it's this one, right? You will be calculating this by ICP. So you don't need to process all these output of your sensor, right? You just need to process like draw input, draw sensor information on a different way on ICPs, and this will give you like a function that calculates like what is the transformation between these two observations. There's no odometry. It's just based on aligning transformation, right? So this is usually what you will be using in PostSlam. Okay, let's do a short break, and after that we will continue with mapping. I'm going to explain it briefly. So, okay, let's do a 5-minute break. Okay, let's continue with the class. This is going to be a little more explaining the story more than working with the equations. I think we are almost done with equations for this course. So what I'm going to do is just go over the class notes, right? And I'm going to discuss them a little, right? So you have them in Canvas, but well, we will discuss based on this. You also have a description of maps in Chapter 9 in Probabilistic Robotics. I think it's a little outdated, right? Because they are talking about grid maps and two-dimensional things. So it's good to grasp the idea of exactly what we are doing, right? But then take this lecture as an introduction, right? And then mapping can change a lot, but the idea it stays the same. It's simply going to be a little different. Exactly, we are not going to have occupancy grid maps, but we are going to have different structures to handle the map, maybe in 3D, maybe in 2D, doesn't matter, right? But the idea is that we still need to think about a map as a probabilistic random variable, right? And after some evidence, now it's less the evidence, the variables that we need to estimate, but after doing some optimization or inferring based on a graph, we are going to get a solution, right? Okay, so let's get into this. So why do we want maps, right? So, well, the first question maybe is, what is exactly a map? Right here, what I draw is this kind of map of the class. Maybe? Well, a little. So this could be blueprints on a building, right? This could be anything. We are very used to use maps, but we don't really think that they are an abstraction of the real environment, right? So when we see a class, I mean, when we see a map of this, with some imagination, you will see that this is a class, but maybe you see the blueprints on a building, and you still know that, oh, okay, so this is a room, this is a corridor, whatever, right? So at the end, these are useful representations, right? In SLAM or in state estimation, this is also going to be true. What we did before is abstract this representation, so it has no physical meaning. A sequence of landmarks, right? A map is a set of landmarks. But what is exactly that, right? Just points in the space, right? With maps, or let's say this new description of maps, there's a tighter connection with actually real interpretation, right, of these environments. Okay, so then, if we get back to all the things that we have discussed, right, like SAM, SLAM, all these things, then why do we really want just to calculate maps, right? So we were discussing two things. The first one is we were marginalizing our landmarks, and then what we get as a result when we were doing SLAM, if you remember, is the estimation of a trajectory, right? We were using landmarks, but then we were marginalizing, and still we get a solution. The second one is what we have described earlier, right? So it's point cloud alignment. Now, forget about landmarks. We are not considering them, and the only thing we take care about is aligning whatever point clouds that we are asked, right? So in this case, this will be a detection of. So this will be when we detect a loop closure, then we simply make it align, make it fit, and then our full trajectory is going to be updated, right? So in this second case, we don't really need maps, and in the first, I mean, maps are kind of, well, let's say our representation, and in the first one, well, we were not using them because we were using landmarks, and then we were forgetting about them, right? So then the question is, we have discussed what happens with point clouds, right? How to align them. But there's another alternative, right? So if you want to imagine this will be the scan-to-scan problem, right? You just have a scan, whatever sensor is giving you. You have a second scan, whatever the second observation on the sensor is giving you, and you want to align them. Now, maps, how can help you just to improve this, right? So instead of that, you can think about it as an improved way of aligning poses, right? So instead of aligning with respect to one observation of the a sensor and a second observation, what you align is a map, right? A physical representation, now measuring like obstacles or points in the space that are occupied, and then your sensor is going to give you like range estimation or a range measurement. This with respect to whatever observation you have, right? So you go there, and instead of matching to maybe noisy sensor information, you match one map against the sensor, right? So you can get the idea that this will be a little more precise. And on the extreme, we can be doing map-to-map alignments. So I have discussed, so what happens when you have a kind of a sparse map, right? I don't know, laser in general, it's not a dense, it doesn't give you, LiDAR, I mean, it doesn't give you like a dense point cloud, dense point cloud of the environment, right? So maybe what you want to do is you accumulate all of them in some sort of a minimap, you accumulate a second minimap, and then you do point cloud registration with this denser. So if you think about it, it's a improved observation, right? But for that, what you will need to do is create a map, accumulate all this information on a meaningful way, right? So maps are not just representations for us to navigate and do things, right? It's also going to help on the, it's also going to help on how well we can align then later poses. Okay, so, well, here I'm saying this, but I think the idea is kind of intuitive, right? So these agrupations hopefully will be less noisy. Then, this goes a little beyond what we discussed in this course, right? But there's a second step, which is planning, right? So now we have always discussed on state estimation, right? What can we do with this? This is estimation of trajectories, estimation of landmarks. There's a second whole world that we haven't discussed today, but actually it requires accurate maps. It requires accurate localization in order to work, right? And it's all this topic related with decision making. So imagine you have an agent, you want them to take actions, do something like a robot moving, or I don't know, anything else that basically can do things, can execute things. For that, you want to have very accurate state estimation, the better you can have. Right? Usually the problem is related, but let's say that if you give like a good state estimation that is maybe a good map or a good localization, then the second part, this planning part or decision-making part, it's going to be better as well, right? So, okay, for now, you can just guess. I'm not going to define any planning thing, but this is one of the main purposes of this. Or maybe you don't want this for this, right? Maybe you want this for other kind of applications, right? Just have your map as a way of interacting with others, right? Or just organizing things, or I don't know. Well, the topic is a little big after that, so what to do with maps, it's very open, right? Depends on what is the quality that you require, right? There's many, many questions here, but still, mapping is really a thing that is required nowadays. Okay, so just as a sum up with this very simple representation, this sketch map, you still get like some information about this environment, right? So there's a couple of tables. Well, there's more, but in my sketch map, there's just a couple of them, and then another table maybe there. Okay, so this is better than nothing. Would you agree that this is better than having here landmark 1, landmark 3, landmark whatever? How are they connected? Is this a physical object? Is this something that you can traverse? Landmarks are abstract things that help on the state estimation, but it's not really helpful in other way, right? Especially for decision making. Okay, well, this is just food for thought. Think about it. Not required for this course. For this course, we just want to have the best estimates, right? And this is just an alternative for doing that. So then the question is, how do we compose a map? There's two options. The first one is we have perfect information. We have perfect positions of our sensors, right? We know the exact poses that from where each of the sensors were giving, and then we just accumulate points or well, whatever measurement is from the sensor. And then there's an alternative, right? So we don't know our true trajectory. We do SLAM, as we have discussed, like in many lectures, and that's kind of the best estimate that we can get. And once we have this best estimate, you can assume that this is known poses, right? It's not exactly known, but you can say that they are close to ground truth, right? And once you have that, then we do this little assumption saying, okay, so now positions from your, let's say, the trajectory, it's going to be known, right? Either of these two cases, what they require to calculate the probabilistic model is that. So we are giving some observations, and we are given a set of positions. And from that, what we are going to describe is the distribution of this map. Right? And then we need to discuss exactly what is this M. Right? We know set of landmarks, but we haven't discussed any other thing. Right? So today, the objective will be not just working a little on the numbers and working a little with the equations, which is what we are going to do for one particular case, but think about this new paradigm. Right? So now what we want to do is estimate this distribution. This is the corresponding graphical model. Right? So we have like some positions. Right? We know that there's a, connection. We have some observations. All these things are known, right? That's what I'm writing them. And then the only thing that we need to estimate is map, right? So the problem seems easier. It's exactly, it might be easier than solving the thing simultaneously, right? Solving your trajectory and solving your map at the same time. But still, we need to do inference, right, to calculate this map. There's still going to be some noise here that we need to take into account. Okay, is this idea clear on what is a map, and then given all the things that we have discussed in this course, how we can calculate on the same fashion, right, just this distribution of the map, right, because this is, I would say that this is today's class, this thing. Okay, I guess that's a yes. So let's continue. What are map representations, right? This is a hard question. What I did here, I guess you can do many other classifications, but I separated them into different classes, right? The first one is explicit map. Here, what we have is explicit entities like a line or objects or surfaces, right, that are basically describing like any object or any obstacle that is there in your scene. If you think about it, we are just simply describing how this space is occupied, right? How is the environment? So this is a description. And the second one is implicit map, right? So in this case, we don't use any geometric feature. We don't use any known thing that can be described. This is a little more general, but it's more powerful at the same time, right? So implicit map could be just a point cloud, right? So you have millions of points, and that's your map. Well, then maybe you need to do assumptions on let's say, connectivity between points, but still, this is quite powerful description. We could be using here a grid, right? So you have your space, two-dimensional space or three-dimensional space. You discretize it, and then decide if one cell is occupied or not. You can move this to more efficient data structures like voxels or octrees, whatever you want. There's another very famous or very used approach, which is the signed distance function, right? So here we are entering slightly the graphics topic. I'm not really gonna get like too deep on this, but basically the map representations are also described by other fields, right? Not just in our field on state estimation, right? Then here what we need to go is maybe to the graphics community or others, and then they use these kind of other functions, right? Distance signed function or the truncated version. There's a whole family of these. This is a nice representation because what you have is still a grid of your volume or plane or whatever you have. And each value here, it's giving you the distance to the closest surface, right? So with this, what you have is a bunch of values, some sort of a grid, but it's not a binary decision, right? It's more just distance, what is your closest point. Okay, so all these things, really used. I'm sure that if you have worked with maybe you have heard about some of these methods before, but for map representation, yeah, you have here a lot of freedom, right? So almost any representation here can be useful. At the end, what we want is to capture this physical meaning, right? So we are here in a room, or we are here outside. How is this going to help our sensors? In this case, we just Maybe we want to add here like texture, right? And then do a different kind of mapping if we are actually doing visual SLAM, right? So maybe your map is just a set of keyframes. That's very open. It's a very open question, right? But it's anything that it's going to help you later somehow, right? So the map is giving information, right, on the environment. Here, there's a definition, and this is what we will be discussing today. Again, just think about this not as the definite and only way of mapping, right? This is just an introduction. Later, well, as I said, the topic is very wide. So this is what is called Occupancy Grid, right? The idea is very simple. So you create a grid, and then here what we are deciding is each of these cells has two states, a binary state. It's either occupied or it's either free, right? So this is kind of intuitive idea. You just take your whole room and then or all those cells that correspond to, I don't know, this table or whatever are going to be like value 1. And all those that we can traverse, or the robot can go around, or our sensor doesn't see anything, doesn't observe anything, those are going to be free. Okay, so this is a way, a representation. This is not the only way. As I said, there's many of them. You can think about landmarks also as another way of mapping. But the problem is that here what we were doing is we were abstracting all this physical meaning, right? Then landmarks were just like positions for some given points, not all of them. Well, positions or, yeah. So what is this here? If you have like, okay, all these things are kind of empty, and here you have like some obstacles. Maybe if you had a map of landmarks, you will have here landmark 1, landmark 2, and maybe landmark 3, right? So you will have that is not really descriptive enough, right, if you want to do other tasks. Okay, so with this definition of what is occupancy grid, binary states of cells, let's start discussing a little, right, on how to calculate like what is the best estimation of our map. If you think about the complexity of the problem, this problem actually it's complex. So even for this very small map, just imagine 6 by 5 cells, right? We have to estimate what is the state for each of them, right? And the combination of all possible maps for this small reduced grid map is huge, right? So imagine you just start doing the combinations of, yeah, this thing occupied, now this free, right? You create all the possible maps, and that's absurdly high number, right? So we cannot really treat this like brute force. It's not possible now to go over all overall state, possible states in your map, right? And just calculate which is the most likely one, right? This is not really going to help. So what do we do? As always, we take some approximations, reasonable approximations. Who has like a guess, right? So first thing that comes to your mind to do an approximation. Okay. How many observations for each cell? Yeah, but you need to forget now about landmarks. Landmarks are gone. It's not really. Okay, maybe that heuristic will work, but remember always that what we are going to have is like some sort of range observation, right? So maybe we cannot really observe like each landmark, each cell here. What we are going to be observing is, let's say, a sensor, right? Giving you like, if you remember, oh, no, it's not here. It's here. hold on, because I think this is an important question. So let me, yes, this thing. So this is what we are going to have. Our sensor is going to give us like when a ray, laser, has hit with an object, right? If you think about cells inside here, you will not be observing each of them directly, right? So I think no, we need to stop thinking about landmarks here. Forget about these points. We were just going to have like a bunch of observations. And then with this, we will create our map to our best estimate we can. So to solve this problem on high number of combinations, one thing that we can also do, right, rather than thinking a little, okay, so how can we reduce number of observations, it's assuming independence, right? That's another alternative to do. So what this means that here we have this distribution of our map, right? And here, this is the joint binary state of all cells, whatever number it is. And then instead of doing that, what we say is that each of these cells is going to be independent, right? It doesn't matter if there's an object next to your cell, right? We know that that's not true, right? Because if you have a table, it's going to be more likely to have some object next to it, right, for instance. But in this case, what we are saying is it doesn't matter what it's in your cell. It's not going to affect the distribution of others, right? So you're always treating your map just as independent cells, right? This assumption, if you remember, we did for we did this in many places. For data association, we did it for sure, maximum likelihood. We also did this for the EKF SLAM. When we were updating different observations, do you remember? We were assuming, okay, so they are going to be independent, right? Now, in this case, it's different because now it's not observations, it's cells, right? Cells are going to be different, are going to be independent. But this simplifies a lot the problem. So now this distribution, it's going to be factorized by a bunch of these probabilities. We are going to see what they are. But, well, this is tractable. Now this previous distribution was not tractable because of the state space, right? That was too large. Okay, and then what else? We need an inverse model, right? So we cannot really calculate this. What is the probability given an observation? Remember that observation is this. You just get a range, like a position from your sensor, and from here you need to say, okay, is your cell occupied or not, right? So that's kind of a strange. But what we can do is the opposite, right? As always, we can use Bayes' theorem, and then this distribution is a little more reasonable, right? So knowing if given like a state of your cell, you can say if you have observed something or not. And the idea behind is ray tracing, right? If something is occupied, you are going to hit an object. If something is free, your observation should keep going, right? So here in this cell, if this is free, what you are going to be seeing is that, well, your observation doesn't stop here, right? But it simply keeps going. So you do ray tracing on this, and those cells that are free, you should just keep propagating your, let's say, observation until you hit something that gives you a value. So that means that there's an object there. Okay, so that's intuition. So yeah, we're going to have this. I'm going to describe it in a moment. Now, our state variables are binary, but we can also define them as random variables. And then what we can say is the probability of being occupied. Right? So our state variables are binary, but we can define just what is the probability of this cell being occupied. Right? We are not going to have complete certainty. Right? If we had, then the problem is easy. It's all 0 ones, and then we go away. But as I said before, there's noise. Right? There's random variables that are going to be affecting. So we need to treat our map as a random variable as well. Right? And in this case, it's going to be the same kind of, it's almost going to correspond like states in this binary state, but for probabilities, you can say that, okay, 0, for instance, is free, and probability of being occupied is 1, right? And then what happens when you have something in between? Then we cannot say that if it's either occupied or empty, right? And that's kind of makes sense, because if you haven't observed something, imagine what is behind that wall, right? That wall there. I haven't never observed this, right? So how can you say anything about it? How can I say that this is going to be empty or this is going to be occupied, right? So this is what this uncertainty is just saying, that the probability is going to be like not really defined, right? And this is also important. Okay. Then for binary variables, we are going to be using a different kind of distribution. Now we don't have a continuous distribution, so forget about normals, but actually what we are going to be using is log odds. It's very useful anytime that you have a binary variable, right? So this is going to appear. And in this case, it's just this, right? So it's the probability of being occupied divided by the probability of not being occupied, right? Or if you want this divided by 1 minus this. Okay, so what is an interesting thing about it is that there's a transformation when you apply the logarithm to this that you will see that it's going to be very useful for us, right? So if you had this random variable just expressed as probability of being occupied and probability of being free, this goes from 0 to 1, right? There's not really much you can do. You need to stay in that range if that's a probability. But now this new defined probability, actually the image of this is going to be to the minus infinity to the plus infinity, right? So we are just changing slightly the domains. And the interesting thing is that there's an inverse, right? And this is going to be useful for us because what we are going to be proposing for occupancy grid map is to use log odds probability, and then if you really want to calculate what is the probability of some cell, then you do the inverse. But in general, it's going to be expressed with these L variables, right, with the logarithm. Okay. For this, we are going to be using a version of the base filter, but now it's for binary variables. It's very similar. Well, after doing all these classes before, all these lectures, I'm sure that you, well, all these terms are kind of familiar, right? So, as always, we calculate a belief, in this case of the map. This is what we said before, assuming independence, right? And then what happens for one cell? Remember, we are going to be multiplying all this, right? But let's analyze the problem for one cell, right? So for one cell, this is what we want to calculate. This is the belief. So what we need to do is some manipulations, right? Here we apply Bayes' theorem. You can do the derivation later at home if you want. But basically, after doing some manipulations, what we want is to obtain this likelihood, right? And then we are going to have other that are not important. So why is this interesting? It's interesting because usually beliefs here use the full trajectory, use the full observations. But what we want to calculate is this function that only takes into account the current position, this cell, that this is the one that we are analyzing, and the current observation, right? So this is all of them at time t. So if you want, we have separated all the previous history into these terms. You know that usually in the Bayes filter, this is kind of recursive, so all the previous history, it's going to be our previous belief. I'm not doing any spoiler here. No? No. So usually in Bayes filter, we always get the previous belief, right? And that's why it was an iterative thing. So here it's happening the same, right? I'm just moving this a little faster. So here we have all this previous history divided by something, and then here this is the interesting part, right? So for this one cell, this is the likelihood. We have discussed here that this is a little complicated to calculate here, right? this is complex. So how can you tell if one cell, what is the distribution of one cell given our observation? It's much easier to calculate this, right? Given a cell, so we are going to assume whatever value it is, if you have an observation, right? So that basically means have this observation traverse your cell. If it has, maybe it's because it's empty. Has your observation just give you like a return close to your cell, let's say an object being on your cell, that means that might be an object there, right? That might be occupied. So this likelihood function, it's intuitive and it's going to be easier for us to calculate. So what it means, okay. Yeah, so what it means is that this term, after separating all the previous observations and all the previous positions, we need to apply Bayes again, right? So that's what I'm writing here, right? In this, actually I can write, oh no. No, okay, too bad. So I take this part, just considering the current observation and the current position. We apply Bayes theorem, right? And then what we get is what we were discussing before, right? A likelihood function that now depends on your on the observation and your state, and then it gives you, and then, well, other terms that they are not complicated. So this is going to be this likelihood function. If we take all this and substitute in 1, then what we get is the following, right? I'm only adding here like those terms. So I'm taking this and I'm substituting this part, I mean this into this. So no, this thing into this, right? Right, and then we see that some of the terms simply go away, right? So if we assume that this is a Markovian process again, this distribution, which was obtained by this likelihood, and this distribution, considering all the previous history, so this is kind of the same thing, right? You just care for your current observation, you just care on your current position, right? So this goes away. I'm just going to call this probability of each of the cells. And then you can do the same for the negated, right? So that was for the positive of being occupied. This will be positive, the probability of not being occupied, right? So we do the same kind of substitution. And then if you remember, what we are interested in is in log odds, right? So that means that we need to take this, we need to divide each of the terms that we have find here, right? Like this one and this one, right? We take these probabilities of MI after doing some manipulations and some assumptions, like Markovian assumption. And I think this is where things are going to start making sense, right? So we do here this, and then we can group things this way, right? So you do all these, well, this is just, I'm substituting. We rearrange things, and then we obtain this, and this really has like physical meaning, and I would like to discuss this with you, right? Everyone should be like, have a clear idea of exactly what we are doing. So this is the prior. This is whatever previous or whatever, prior guess we have of our cell. Remember, this is log odds, so that's why we are dividing. We have the current update, so we have the log odds for whatever new observation we have obtained. And this is the recursive form that we were talking about before, right? So this is going to be whatever previous belief in log odds. Fine, it's just going to be there, a recursive term. And then the important one is going to be this one, right? It's going to be the likelihood. So with this new observation, how you're updating your map, right? And then this was whatever initial value you have for your cell. Maybe you start with 0.5, which in log odds is, okay, I don't know. Okay, so we have arranged things on a nice way. So what we can do now is just apply the logarithm. And with this, you will see that this gets even more simplified, right? The problem actually with multiplying all these things is that, so imagine that you are very certain that some cell is free, right? So maybe this is close to 1. Or no, that will be, yeah, this is going to be very close to 1. And this means that this is going to be very small, right? So you're going to start having instability, numerical instability here, right? So the more certain you are, that means that probabilities are closer to 1 or to 0. So here, that's a big problem, right? Dividing by things very small is very bad. Dividing by a 0 might round off and be exactly 0. Well, that's not that bad, but still. So do the same thing. We apply the logarithm into the previous one. And then what we get is even a nicer way of describing this. So in log odds, this is going to be our initial guess of every cell, right? Whatever initial number you can give it. You can start, all of them are free, all of them are empty. Nothing definite, right? So that's going to depend a little on you. This is the L0. It's always going to be here. That's the only thing that we need to cross all the time. There's going to be the inverse sensor model, right? So with this, I'm going to explain what it is later. But the idea is that it's ray trace. So you ray trace your observations, and if cell is free, you should go. You should, your observation or your laser should just continue its path. If there's an obstacle, that means that you should be seeing an observation at that point or at that cell. And then this was the previous estimate, whatever it is. Right, so this is basically it. Previous one, the inverse model, and then L0. And if you ever want to calculate this in probability, so you just need to do the inverse. But in general, you are going to maintain these values in log odds. Right? It's going to be a little more useful because then later you can use them like in a better way. So this is the algorithm, nothing more. Is everybody like have followed until here this version of Bayes filter applied to log odds? Not every detail, but the idea, right? The idea of we have a previous thing, a previous belief. We have a prior. This is kind of new, but it makes sense after doing this derivation. And then we have a likelihood function. And this is an iterative process. The more observations we are, the cells are going to change their value, right? Is everyone, because this is the important idea of occupancy grid mapping, right? Regardless of, okay, I didn't follow Bayes' theorem here, subindexes, right? Is the idea clear that this is going to be a recursive algorithm, right? Okay, good. Good. Still, what is a consequence of this? Right? It means that you cannot, even if you had perfect information, even if you had like perfect information in your poses, because of the nature of these random variables because of the nature, you cannot really say that your map is perfectly known, right? Because it always depends on a sensor, and the sensor is going to be imperfect, right? So for that, we still need to treat this probabilistically. You cannot really say, yes, I think there's a team 4, yes, when you are doing mapping, right? So you can go there and say, oh, team 2, sorry. So you go there and say, yeah, I'm going to do mapping, right? So this is what I was discussing a little with you. So you can do that, but then that means that if you do it this way, your inverse model is very, very accurate. Right? It's extremely accurate, and then it doesn't really matter what it's previously seen. But if it's not so much, then you might want to take into account what you have estimated before, right? So, well, maybe this is a little advanced. I'm not sure how far you have gone on your project, but you might want to take a look at well, how these things are done, and then, I don't know, discuss at least on this. Okay, so then let's go for the algorithm, right? The algorithm is fairly simple. We basically take our previous estimate of occupancy on cells. We take the current position, which we know, by the way, and then we take the current observation, right? And then basically what we need to take is only update those cells that are in the perceptual field of set T. That means that we only update cells that we have some evidence, right? If that cell is not really affecting the observation, why should we update it? So that's not, it's like, I'm looking at that way and I want to optimize what is behind me, right? So you cannot really do that. And then if not, you just keep whatever previous estimate you had, right? It might be like, we don't know, like 0.5 probability or something, right? And this is the example of the perceptual view, right? So here we have our sensor. In this case, it's not 360 degrees. Maybe here we have like a bigger room, and then the perceptual field is not really like aperture, but maybe like, well, other features here, or max range, or whatever. And then basically we are going to update all those cells that are here. So for instance, this one is not on the perceptive field, right? So we cannot say anything about this. But we can say something about this, right? The observation, maybe we are getting an observation here, right? But we can still say things. We can say that it's likely, right? Because we always have, it's likely that your observation gets through this cell if this is empty, right? So then you will be reinforcing this idea of the probability of this cell is going to be empty, right? In case that you get here an observation. The same happens for these ones, right? So here, if you get like an observation that is close by to this cell, then the log odds values should be changing, reflecting this, right? So then, well, the logarithm of the probability should be, well, closer to probability of being occupied. Okay, so this is also an example. So what happens with the previous one? So we have this some sort of inverse model. In this case, we have L3. I mean, all our previous values were 0, right? I mean, in this case, this was, the two of them were free. So this, no, 0 was like we didn't know much. And then what we add here is L being free. So in this case, this likelihood function here, this inverse model, or in other words, this thing, right, gives you a value of 100. This is an example. I'm not really doing but you could be calculating this properly. So that means that if this is free and then whatever minus LO, then you get your new log odds to be minus 100. A good thing is that this can go to minus infinity and you don't have numerical issues, right? Because then the inverse function is just going to take care of this for you. And then the same goes for occupied, right? So the more evidence you accumulate here, this number is going to grow and grow. But it's more stable than just updating like things being multiplied, right? So we are just kind of unwrapping this space. In this logarithmic space, things are better suited for not doing like errors. And well, we do this enough time with enough observations, and then finally we'll get like a nice map, right? Okay, so this was the brief introduction to it. You have a nice explanation on the book also if you want to go more on the details, right? So there on the book they will go over these equations. You can expand them at home, right, following this, and you will still get these results if you want to do it. On the book there's more explanations on this. And then the other interesting thing and the other interesting idea that I commented is that actually this is just the starting point, right? Later, you might have other map representations, right? Like DSF, doesn't matter. You need to think on ways of representing it, right? So this is just an introduction. The occupancy grid map is not the only way to do mapping, right? I'm not explaining all of them because, well, we are kind of short in lectures, but the important thing is that maps should help you to whatever task you have. If it's just localizing, maybe you don't need physical meaning. You just need to have some landmarks here and there. If you want then to do some actions, then you might want to have like map closer to a physical environment, right? So this is another extra dimension for you to design, right? Not just, okay, I'm going to do SLAM here, but why do you want this? Do you want this because you want to have best accuracy? You want this because then later, I don't know, maybe it's going to be used for some other task like inspection or whatever, right? So this is extra things for you to think about. Maybe for SLAM, as I said, you just use whatever is more accurate, and then you think on another thing for maps. But take this class, today's class, just as an introduction to mapping, right? It's not only grid mapping, right? There's many other things. And for that, you will need to think exactly what is the characteristics of each of them, right? Think probabilistically, and then, okay, well, probably look at other papers. Okay, so that's it. Unless, well, there's any question, comment? No? Okay, I guess that's good. We are going to be here anyway for some time, and I'll see you on Monday. On Monday, I'm also going to do like more a discussion, right? Not even, for sure there's not going to be any equation. I'm just going to discuss a little on Visual SLAM and current trends, and this is going to be last class, next Monday, right? So see you on Monday.